Take a look at the unit 9, the exponentials and exponential graph unit. So some of the properties, if you ever raise anything to the 0 power, it's always equal to 1. A to the negative n. Well, remember that negative exponent will always send things to the denominator. And likewise, a over, or 1 over a to the negative n, that'll send a to the n back into the numerator. It's like a to the n over 1, but nobody writes the over 1. It's just understood to be there. If you have a times b raised to the n power, remember this is where you can kind of distribute that in because there's not anything between the a and the b. Similarly, I'm just going to go straight down. If you have a divided by b raised to the n power, that's like saying a to the m over b to the m. Here, when you have a to the m times a to the n, remember this is where you can just add the exponents. And so multiplication turns into addition, and so this division problem right here will turn into a to the m minus n. And then if you have power to power, remember you just multiply those two things together. So let's start using some of those properties. B squared, b to the fourth, and then that's b to the first, remember? So in other words, how many total b's do you have? You can just add the exponents. So 2 plus 4 plus 1. Probably a lot of you guys would already do that in your head and realize there are 7 b's there. 39. So we can distribute this 2 into all these pieces. So that will be x to the fourth, y to the negative fourth, over y to the negative 6. Now, these negative exponents, they're going to switch places. So we end up with x to the fourth, and then that y to the negative 6 comes to the numerator, y to the fourth goes to the denominator, and now we've got 6 y's in the top, 4 on the bottom, and these can cancel, and what you're left with, x to the fourth, nothing cancels, we're left with 2 y's in the top, and nothing in the denominator, so we can write it just like this. So here, first step, let's distribute that 2 in, so we end up with c to the fourth d squared times cd to the seventh, and now just combine the c's, so there's 4 c's here, 1 c here, so we have c to the fifth. There are 2 d's, and then 7 d's, so that'll be d to the ninth. Here, let's look at these negative exponents, so that one, that one. So what that tells us is that those things need to switch places. So we end up with 5. That b to the seventh will stay on the top. That a that's in the denominator will stay put, but then this a to the fifth, remember, that's going to come down. And then this b to the negative third is going to go to the top and turn into b to the positive third, right? So remember as well, when they switch places, that's how you get rid of the negative exponent. Now let's just combine the like terms. We end up with 10 b's in the top, 6 a's in the denominator, and that's all we can do. So when we start doing these exponential graphs, remember we're just going to plug values into this function. This is where Desmos can come in very, very handy for us. So what I'll do, we want 4 times 0.5, 4 times 0.5, and then we're going to raise it. All right, we're going to raise it. So let's look at our options. The first one we're going to do is raise it to negative 1. So let's plug in negative 1, and that's 8. So we'll write that in. And Desmos is very powerful in the sense that we can just now go in and delete this to the 0, so that's 4. I can just keep using the same thing, just delete, oh, put the 1 there, so that's 2. You start to probably see a pattern. Oh, actually, I don't know why that's just 8. Apologies, I wrote the wrong number in there. Probably starting to see a pattern developing. So there's 1. And then those of you guys that are good at spotting patterns probably already have a good feel for what's about to happen, but we'll finish it off just in case. So we got a raised to the third power, 0.5. So you can see it's decreasing, it's getting cut in half each time. So now we plot the points, negative 1, 1, 2, 3, 4, 5, 6, negative 1, negative 8, 0, 4, 1, 2, 2, 1, 3.5. So what we have here is exponential decay, and let's decay by 1/2 or 0.5. So the asymptote, remember, what line will this get really, really close to? So let me go back in here and clean this up just a little bit. Right? And the asymptote here, this might actually be one, we're looking at Desmos, could be really, really helpful. So y equals, and then we'll go back and we'll put x in here. If we look at that graph, it looks like that's going to get really, really close to the x-axis. Remember, we did this in class. If we zoom in, zoom in, zoom in, it's getting closer and closer and closer to the x-axis, but it never actually crosses it. So the asymptote here is the x-axis, which is also written as y equals 0. The y-intercept, it's just the point where it crosses the y-axis. That'd be the point 0, 4. All right, so we're solving exponential equations. Make the bases the same on both sides. So in other words, we got to figure out, can we turn this into 5 raised to some power? And 125 is actually 5 to the third. And once we have the same bases, remember, we basically get rid of them, and we just set the exponents equal to each other. So x to the third. Sometimes you have to do both sides. So this is actually 3 squared raised to the x plus 1. And then 1 over 27 will actually be 3 to the negative third. So since the bases are the same, I can get rid of those, and I end up with negative 3x equals 2 times x plus 1. So distribute the 2. So 2x plus 2 equals negative 3x. So I'll subtract 2x from both sides. So negative 5x equals 2. Let me come up here with that. Divide both sides by negative 5. So x equals negative 2/5. That one's a little bit tricky, but remember 3 to the third is 27. I need to get that 27 in the denominator. So how I do that is by using that negative third power like I did in 44. In 45, I believe 64 is the same thing as 4 to the third. And so I don't even have to touch the piece on the left side of the equation. Got the same base now, so I can get rid of it. So x plus 2 equals 3 times 5x. Or in other words, x plus 2 equals 15x. Subtract x. So 2 equals 14x. Divide both sides by 14. So here x equals, it'll end up being 1/7 if you simplify 2 over 14. This is where we went to Desmos and we did some growth and decay models. A, recall, is the initial value, or the starting point, and B is the growth or decay rate. If B is larger than 1, then you have growth. And remember, the rate, or 1 plus the rate, equals B. If it's between 0 and 1, this is decay. This is a decay model. We actually saw that on the previous page. You see how that rate of 0.5, right, this is the same thing as 4 times 0.5 raised to the x. That's less than 1, so this was decay. Sure enough, that graph went down. The initial rate was 4 here. All right, so we'll go back to this model. And remember, 1 minus the rate is equal to B here. So you got to do a little bit of work to get that B value. So the world population in 2000 was approximately 6.08 billion. So there's an initial rate, A. The annual rate of increase was 1.26%. So find the growth factor. So the growth factor B equals 1 plus, right? It's increasing. And the rate, we need to turn that into a decimal. So 1.26 equals 0.0126, right? Move the decimal over 2 spots. So 1 plus 0.0126. So here, B equals 1.0126. Right, the function that will model this. So that's y equals the initial rate, 6.08, times 1.0126 raised to the x power. Predict the world population in 2020. So this is one where I would go to the graphing calculator. So we have y equals 6.08 times 1.0126. Let me make sure I did that right. 0.126 to the x. Now, as is, we don't see it, so something's up with this. Let me try this again. 6.08 times 1.0126. I'm going to raise that to the x. There we go. Now we're starting to see a picture of the graph. And we want to figure out what's the world's population in 2020. So in other words, after 20 years, right? And that's because we started in 2000. So after 20 years. So remember with these graphs, time is the x-axis. So we're basically just going to drag a point until we get to the year quote unquote 20, and that's 7.8. So the point is 7.8 now. So at 20 years, we have 7.8, but remember, it's not just 7.8 people, it's 7.8 billion people. So that's only a few years from now, right? So here, computer valued at 4,000 depreciates at a rate of 18.2% per year. So find the initial value. So the initial value was 4,000, and this is a decay factor because it's going down, which means we need to do 1 minus 0.182. All right, and it's 0.182 because, again, 18.2%, we need to turn that into a decimal. So move the decimal over 2 spots to get 0.182. And what that'll end up being is 0.818. So there's your value for B. So the function that models the value of the computer would be 4,000 times 0.818 raised to the x power. So find the value after 3 years. So what we could do here, if we don't want to go to the Desmos, we know that x is the number of years. So we could just do 4,000 times 0.818 raised to the third power, because x is number of years. So grab a calculator, plug that in. What that should be is 2189. So it'll be worth about $2,200 after 3 years. The other option, go to the graphing calculator, just drag your point until it gets to 3.